What if everything you see, touch, and feel, your body, the stars, even the vastness of space, wasn't actually three-dimensional? What if our universe is nothing more than a grand projection, a cosmic hologram? Tonight, we'll explore the mind-bending idea that our 3D world might be an illusion, and how scientists are trying to uncover the truth. Chapter 1. The nature of dimensions. Imagine a point. No width, no height, no depth, just a position. That's 0 dimensions. Add a line, and you get 1 dimension. Length. Add width, and now you're in 2 dimensions, a flat square. Add height, and suddenly you're standing inside a cube, a space you can walk through and touch. This is the world we know, 3 dimensions. We move left and right, forward and back, up and down. It feels natural, it feels obvious. But here's the mystery. Is this really all there is? From simple shapes to impossible visions, for centuries, mathematicians and dreamers wondered what comes next. If a cube is the 3-dimensional version of a square, then what happens when you extend a cube into the 4th dimension? The answer is something called a tesseract, or hypercube. We can draw projections of its strange, overlapping cubes connected by lines, but we can't truly imagine it. Our brains evolved inside a 3-dimensional world, so the 4th dimension is forever slippery, forever beyond reach. And yet, even though we can't picture it, mathematics says it exists. A Victorian obsession. In 19th century England, the idea of higher dimensions became more than a curiosity. It turned into a cultural obsession. Writers, scientists, and spiritualists all seized on the 4th dimension. Some believed it was the doorway to the diviner place where souls might reside, invisible but real. Others treated it as pure math, an elegant extension of geometry. The fascination spilled into novels, sermons, even art. For many Victorians, the 4th dimension was a symbol of hidden truth, something greater than the ordinary eye could see. Riemann's revolution. Around the same time, a German mathematician named Bernhard Riemann reshaped the very language of space. Before him, geometry was simple flat planes, straight lines, and right angles. As Euclid described 2,000 years earlier, Riemann dared to imagine new geometries, surfaces that curved and bent, spaces where parallel lines met or drifted apart. His work opened the door to modern physics, because suddenly space itself didn't have to be flat. It could warp, twist, expand. This wasn't just abstract math. Decades later, Einstein would use Riemann's geometry to build general relativity, the theory that explains gravity as the bending of space-time. But here's the twist. Once you admit that space can bend, and that more than 3 dimensions can exist, you also open the door to something far stranger. Why dimensions matter. You might wonder why care about dimensions at all. Isn't it just an abstract puzzle? Not quite. Dimensions tell us how the universe stores and shares information. They define how particles move, how forces act, and even how energy spreads. For example, the laws of thermodynamics, the rules of energy and heat, depend directly on dimensionality. If we lived in 2 dimensions instead of 3, the very behavior of atoms, heat, and life itself would be radically different. Stars might not form. Planets might not exist. The universe as we know it could collapse into chaos or perhaps never exist at all. So dimensions aren't just a trick of the mind. They are the scaffolding of reality. A quiet question. And yet, hidden behind all this, a quiet question lingers. How do we know the 3 dimensions we experience are fundamental? What if they are not? What if, like shadows cast on a wall, our 3D world is only a projection of something flatter, simpler, more fundamental? Setting the stage, this idea that the universe might be a hologram, a grand illusion of depth, sounds impossible. But physics keeps circling back to it. From black holes to quantum theory, clues keep whispering that our world might not be as solid as it seems. But before we chase that possibility, we needed this foundation, an understanding of dimensions themselves. Dimensions are not just directions, they are the grammar of the cosmos, the framework inside which everything unfolds. From Riemann's curved geometries, to the endless fascination with the fourth dimension. Humanity has always sensed that our ordinary view of space might not be the full picture. And as we'll see in the next chapter, black holes, the darkest, most extreme objects in the universe, would force us to confront this suspicion head-on, because inside their mysteries lies the seed of a shocking thought. Maybe our three-dimensional world is not the ultimate reality, but only the surface of something deeper. Chapter 2: Seeds of the Holographic Principle. To understand why scientists began to suspect that our three-dimensional universe might be a projection, we need to look at the strangest objects in the cosmos. Black holes. Black holes are nature's paradox. They are both terrifying and elegant, destructive, and yet deeply informative. They are the ultimate laboratories for testing our ideas about space, time, and information, and hidden inside their mysteries is the first seed of the holographic principle. What exactly is a black hole? A black hole begins as a star. Not just any star, but a giant, massive, one many times heavier than our sun. When such a star burns through its fuel, it can no longer fight against the pull of gravity. The outer layers collapse inward. The star for smaller stars, this collapse might leave behind a white dwarf or a neutron star. But if the star is massive enough, gravity wins completely. The collapse continues until matter is crushed into an infinitely dense point. This is the singularity, a place where the laws of physics as we know them break down. Surrounding that singularity is the event horizon. Think of it as a one-way door. Once you cross it, there is no escape. Not even light, the fastest thing in the universe, can outrun the pull of gravity. That is why black holes are black. They swallow light itself. To us, the event horizon looks like a perfect sphere of darkness. But is it really empty? Or does it hide secrets we have barely begun to imagine? Jacob Bekenstein's bold idea in the 1970s, a young physicist named Jacob Bekenstein asked a radical question. He wondered, what happens to entropy when something falls into a black hole? Entropy, simply put, is a measure of disorder or information. When you burn a book, the ink and paper are destroyed, but the information is not truly gone, it is spread into the smoke and ash. According to the laws of physics, information cannot just disappear, but a black hole seemed to break that rule. Toss in a book, or a planet, or an entire star, and it all vanishes. Where does the information go? Bekenstein proposed something shocking. He suggested that the entropy of a black hole, the amount of information it holds, is not proportional to its volume, but to the surface area of its event horizon. This was revolutionary. In ordinary experience, information seems to scale with volume. A bigger box can hold more books. A larger hard drive can store more data. But Bekenstein argued that in black holes, all the information is smeared across the surface, like ink on a page. At first, many scientists were skeptical. It felt too strange. But then Stephen Hawking entered the story. Hawking radiation and the information crisis. Stephen Hawking discovered something extraordinary. Black holes are not completely black. Thanks to the strange dance of quantum mechanics, they emit faint radiation, now known as Hawking radiation. This radiation slowly leaks energy away. Over unimaginable spans of time, a black hole can evaporate entirely, shrinking until nothing is left. But here lies the paradox. If a black hole evaporates and vanishes, what happens to the information inside it? According to the laws of quantum mechanics, information cannot be destroyed, but Hawking's calculations suggested it might be lost forever. This clash became known as the black hole information paradox. It wasn't just a puzzle about stars, it struck at the very foundation of physics. If information can vanish, then the rules of the universe are broken. The crisis demanded an answer. Painting information on the horizon, enter Gerard T. Hooft and Leonard Susskind, two brilliant physicists who looked at Bekenstein's idea in a new light. They proposed a radical resolution. Information doesn't vanish inside a black hole. Instead, it gets encoded on the event horizon, the black hole's surface. Think about that for a moment. Everything that falls into the black hole, every particle, Every piece of information doesn't disappear into the singularity. It gets painted, in some hidden code, onto the surface. To an outside observer, the black hole is like a cosmic hard drive. The interior is unknowable, but the surface contains the record of everything that has happened. And here comes the breathtaking leap. If this is true for black holes, maybe it is true for the universe itself. From black holes to the universe, this is where the holographic principle was born. The idea that all the information inside a region of space might actually be stored on its boundary. That the three-dimensional world we see could be a projection from a two-dimensional surface. It is like a hologram on a credit card, tilted in the light, and you see a 3D image hovering in space. But the information that creates that image is encoded in 2 dimensions on the flat surface of the card. Could our universe be the same? Could everything we experience, space, time, matter, and energy, be a grand illusion, projected from a distant, 2-dimensional boundary we cannot see? The mystery deepens. At first glance, this sounds like pure science fiction. But the more physicists explored it, the more sense it made. The holographic principle tied together black hole physics, quantum theory, and the geometry of space. It seemed to resolve the information paradox, without breaking the laws of physics. And so, what began as a strange curiosity about entropy in black holes grew into one of the most profound ideas in modern science. It tells us that the ultimate description of reality may not lie inside space at all, but on its edges. That the universe is not a solid stage we live in, but a projection, a shadow, cast from a deeper, flatter truth. A haunting line, a black hole does not swallow information into infinite nothingness. It paints it on its skin. And if black holes work this way, then maybe the entire cosmos does too. This is the seed of the holographic principle, a seed that would grow, in the decades to come, into a full framework for understanding reality itself. Black holes were meant to be monsters, cosmic traps from which nothing escapes. But instead, they became teachers. They revealed that information cannot be destroyed, only transformed. They showed us that surfaces might be more fundamental than volumes, and in doing so, they whispered a possibility that still unsettles us today. Maybe our universe is not three-dimensional after all. Maybe what we call reality is written on a cosmic horizon, waiting for us to decode its message. In the next chapter, we'll see how this principle escaped black holes and began to reshape our understanding of the entire universe. Physics itself would begin to turn flat. Chapter 3. Physics turns flat in the last chapter. Black holes gave us a clue. Information isn't stored in the depths of space, but on its surface. That strange idea became known as the holographic principle. But for many years, it was just that, a principle, a bold speculation. The real shock came in 1997, when a young physicist named Juan Maldacena revealed something extraordinary. His work showed that the holographic principle was not only possible, it could actually describe an entire universe. This was the moment when physics itself began to turn flat. Juan Maldacena and the ADS-CFT breakthrough. Maldacena was working at Princeton when he proposed an idea that would shake theoretical physics. He studied a type of universe called anti-de Sitter spacer, mathematical model of a universe with constant negative curvature, like a saddle. It isn't our universe, but it's a good playground for equations. On the boundary of this universe, he considered a type of quantum field theory called a conformal field theory. It describes particles and forces, but without gravity. Maldacena's insight was radical. These two systems, gravity in the curved 3D space, and quantum fields on the 2D boundary, were actually equivalent. Every calculation in one had a mirror in the other. This became known as the ADS-CFT correspondence. It was the first concrete, mathematical example of the holographic principle in action. The meaning of equivalence. So what does it mean for two systems to be equivalent? Imagine you have two completely different codes written in two different languages. At first, they seem unrelated, but line by line, command by command, They produce the exact same results. They are translations of the same underlying truth. That's what Maldacena discovered. A world with gravity in 3 dimensions could be translated into a world without gravity in 2 dimensions. 2 different languages, 1 deeper truth. A movie on a flat screen for most of us. This still feels abstract, so let's use a simpler analogy. A movie theater. On the wall in front of you is a flat, 2-dimensional screen. Light and color dance across it. But when your eyes take it in, you see depth faces, landscapes, entire worlds. You know it's an illusion, but it's convincing. A flat surface creates the experience of a 3-dimensional story. Maldacena's insight was similar. A 2-dimensional system of equations on the boundary could create the illusion of a 3-dimensional universe with depth and gravity. Our reality might be just like the movie, convincing, immersive, but ultimately a projection from something simpler. Testing the mathematics at first, physicists were cautious. The idea was bold, but was it real? Could the math actually line up? Researchers began running calculations, comparing the 3D gravity side with the 2D field theory side, and to their astonishment, they matched. Again and again, the results were consistent. Problems that were too hard on the gravity side suddenly became solvable on the flat side. Complicated equations untangled themselves when rewritten in the language of holography. The holographic principle was no longer a guess. It was a working tool. Why it matters? Why was this so important? Because it gave physicists a way to connect 2 of the most powerful theories in science. General relativity, Einstein's theory of gravity, which works beautifully for stars, planets, and the universe at large. Quantum field theory, the framework of particles and forces, which explains atoms and the subatomic world. For decades, these 2 theories refused to fit together. But through holography, they suddenly spoke the same language. Gravity and quantum mechanics, long seen as rivals, began to look like 2 sides of the same coin. A shocking implication if a 3D world with gravity can be fully described by a 2D world without it. Then what does that say about our universe? It suggests that the 3-dimensional reality we move through may not be fundamental at all. Depth, space, even gravity itself may only be emergent illusions, shadows cast by deeper, flatter mathematics. Our entire universe might be like a grand hologram, rich, vivid, and immersive, but ultimately projected from a boundary we cannot see. The weight of the idea. Physicists were stunned. The holographic principle had escaped black holes. It was no longer confined to exotic objects in deep space. It applied to entire universes. This changed the way scientists thought about reality. If space and gravity can emerge from information encoded on a flat surface, then maybe the universe is less like a stage we stand on, and more like a story unfolding from hidden rules. It was as if the curtain had been pulled back, revealing that the play we thought was 3-dimensional was written on a 2-dimensional script. From speculation to framework, since Maldacena's breakthrough, the holographic principle has grown into a vast framework. Physicists use it to study black holes, quantum entanglement, and even the early universe. It has become one of the most powerful tools for bridging the gap between gravity and quantum theory. It doesn't answer every question, but it offers a map, a way to translate impossible problems into solvable ones. And beyond the technical details, it carries a haunting message. What we see may not be what is real. Returning to the analogy, think back to the movie screen. You sit in the theater, eyes locked on the glowing surface. You laugh, you cry, you feel fear and joy. The world on the screen feels real. But step back, and you remember, it is only light on a flat wall. Now imagine the universe as that screen. Galaxies, planets, people, all part of the projection. The true story is written elsewhere, on a boundary we can't touch. It's a humbling thought, and a deeply mysterious one. Preparing for the next mystery, the holographic principle started as a clue in black hole physics. With Maldacena's breakthrough, it became a working tool, a bridge between dimensions. It tells us that our 3D world may be no more real than the images on a flat cinema screen, that space and gravity themselves may be illusions. But is there evidence? Can this idea be tested, or is it only elegant mathematics? In the next chapter, we'll explore the experiments, the cosmic clues, and the fierce debates over whether our universe truly is holographic. Because if it is, then everything we know, every step, every star, every thought may be written not in space, but on a flat cosmic surface. Chapter 4. Clues and Experiments. If the holographic principle is true, then our entire three-dimensional reality may only be a shadow of something deeper. But how do you test an idea so bold? How can scientists search for evidence that the universe itself is a hologram? This chapter takes us to laboratories, telescopes, and even the fabric of quantum physics, where researchers have tried to catch the first fingerprints of a holographic universe. And yet, the mystery only grows stronger. The Holometer. Listening for cosmic noise. In the early 2010s, a group of physicists at Fermilab designed an unusual machine called the Holometer. It was not built to smash particles together or to peer deep into the cosmos, but to listen, to search for the faintest tremors in space itself. The idea came from Craig Hogan, who believed that if reality is holographic, then space is not infinitely smooth. Instead, it should have a grainy texture, like pixels on a digital screen. We don't see the pixels of a television from far away, but get close enough, and the illusion breaks. The Holometer was designed to find those pixels of reality. It used two laser beams split into long arms, similar to the LIGO experiment, that detects gravitational waves. But instead of hunting cosmic ripples, it looked for a new kind of disturbance, which Hogan called holographic noise. If the universe were truly a hologram, then space itself would jitter ever so slightly, a faint vibration of information at the smallest scales. Detecting that noise would be like hearing the static of the universe's hidden screen. And yet, after years of data, the Holometer found no clear signal. The silence left scientists divided. Was the holographic noise idea wrong? Or were we simply not listening carefully enough? The cosmic microwave background, a hidden imprint. If experiments on Earth don't give answers, maybe the cosmos itself does. After the Big Bang, the universe was hot, dense, and glowing. As it expanded and cooled, light was released, what we now call the cosmic microwave background, or CMB. This faint glow still surrounds us today, the oldest light in the universe, stretched across the sky. Scientists study the CMB because it carries a fossil record of the early universe. Tiny irregularities in that glow reveal how matter first clumped together, eventually forming stars and galaxies. Some researchers believe the CMB may hold hints of holography. In certain models, the irregularities in the background radiation look as if they were stamped, not from a full 3D origin, but from something flatter, lower dimensional. It's like looking at ripples on the surface of a pond, and realizing they don't come from deep below, but from vibrations along the edge. The evidence isn't conclusive, but it teases us. Perhaps the very oldest light in the universe carries a message from a flat, hidden layer of reality. Quantum entanglement and holography. Another surprising clue comes from the strange world of quantum mechanics. When two particles become entangled, they share information instantly, no matter how far apart they are. Einstein once called it spooky action at a distance. But here's the twist. In holographic theories, the way entanglement works looks strikingly similar to how space itself is woven together. Physicist Mark van Romstank and others have argued that the very fabric of space-time may be built out of entanglement. In this view, geometry itself, the distance between 2 points, the curvature of space, is not fundamental. It emerges from networks of quantum connections. This is deeply holographic. Information stored in flat entangled systems might give rise to the illusion of a three-dimensional world. It suggests that space is not the stage, but the play itself, a structure born from hidden rules of quantum information. Skeptics versus believers, of course. Not everyone is convinced. For some physicists, the holographic principle is an elegant mathematical tool, but nothing more. They argue that while a DSCFT works beautifully in certain kinds of universes, there's no proof it applies to ours. Others are more optimistic, seeing holography as the most promising bridge between gravity and quantum mechanics. They argue that too many puzzles, black holes, entanglement, cosmic patterns fit together too neatly for this to be coincidence. The debate is ongoing. Conferences often feature heated discussions, with skeptics demanding hard experimental evidence, and believers pointing to the growing web of indirect clues. It's a rare moment in science where philosophy, mathematics, and physics collide. The unresolved puzzle. So where does this leave us? The Holometer searched for noise and came back empty. The cosmic microwave background shows tantalizing hints, but nothing conclusive. Quantum entanglement suggests deep connections, but the picture is still incomplete. And yet, the mystery endures. If our universe truly is a hologram, then the question becomes unavoidable. Where is the projector? And who or what built the screen? Is the boundary that encodes our universe a physical object, a mathematical reality, or something stranger than either? These questions shift the holographic principle from science into philosophy. They touch on the nature of existence itself. A pause for perspective. It's important to remember. Science thrives on doubt. The holographic principle is not a proven fact, but a bold idea, compass pointing into uncharted territory. Even if it turns out to be wrong, the journey it has sparked has already deepened our understanding of black holes, quantum entanglement, and the structure of space-time. And if it turns out to be right, then reality itself is stranger than we ever imagined. Preparing for the final chapter. The experiments are inconclusive. The clues are intriguing, but the evidence is thin. The holographic universe remains a possibility, a shadow, a whisper, a suggestion. In the final chapter, we'll step beyond experiments into philosophy and imagination. We'll ask, what would it mean for humanity if we truly lived inside a cosmic hologram? Would it be a new dawn of understanding, or a Pandora's box of unsettling truths? Because the holographic principle is not just about physics, it's about identity, meaning, and our place in the cosmos. Chapter 5, Philosophy, Reality, and the Human Place. For thousands of years, humans have asked the same haunting question: what is real? The holographic principle is not only a scientific proposal, it is a mirror that forces us to face this ancient mystery. If our universe is a projection, then perhaps our lives are shadows on a deeper surface. And if so, what does that mean for us? This is where science meets philosophy, and where physics touches the human spirit. Plato's cave, shadows mistaken for truth long before black holes or quantum physics. The philosopher Plato gave us a powerful image. He asked us to imagine prisoners chained inside a cave. Behind them burns a fire. Between the fire and the prisoners, objects move, casting shadows on the cave wall. The prisoners, never seeing the outside world, believe those shadows are reality. Plato used this allegory to explain human ignorance. We may mistake illusions for truth, unless we turn and see the fire, or, better yet, step outside the cave into the light. The holographic principle echoes this ancient tale. If our three-dimensional world is only a projection, then we may be like Plato's prisoners, staring at cosmic shadows, unaware of the hidden surface that shapes them. Holography and the simulation hypothesis. Today, this idea often gets compared to the simulation hypothesis, the thought that our universe could be a computer program, running on some vast machine built by an advanced civilization. At first, holography and simulation may sound the same. Both say reality is not what it seems, but there are differences. Simulation theory imagines an artificial program, coded by someone or something. If true, then somewhere outside our universe sits the hardware of existence. Holographic theory, by contrast, does not need a programmer. It is a law of physics, a natural structure where information on a boundary generates the illusion of a volume. One is digital philosophy, the other mathematical physics. but both raise the same unsettling thought. The world we touch may not be the deepest level of reality. Does this make life less real or more? Here lies the psychological weight of the idea. If our universe is a projection, does that make it less meaningful? Some fear that it does. If reality is a shadow, then perhaps life is only a trick of light, an illusion with no solid ground. This view can feel cold, even nihilistic. But there is another perspective. Even if we are holograms, our experiences are still genuine. A dream may not be real in the physical sense, but inside it, the emotions and insights we feel carry weight. Likewise, even if our world is written on a distant boundary, it is still our world. The beauty of a sunset, the bond of friendship, the search for knowledge, none of these are diminished. If anything, they become more profound, because they are part of a cosmic tapestry woven from the deepest laws of nature. Perhaps holography does not cheapen life. Perhaps it enriches it, reminding us that we are part of something stranger, and possibly greater, than we ever imagined. Are we confined or connected? Another question rises. Does holography suggest that we are trapped, or that we are connected? One view is confining. If we live inside a projection, then maybe we are like characters in a book, forever bound by the pages on which we are written. We cannot reach the author, we cannot step outside the story. But another view is liberating. If our universe is a hologram, then everything in it is bound together by information on the same surface. That means we are fundamentally connected to each other, to the stars, to the entire cosmos. It is not confinement, but unity. The boundaries of the universe do not imprison us, they hold us in relation to all things. Which view is right? Perhaps both, or perhaps neither. The mystery remains open. Hopeful vision, the path to unity for physicists. Holography carries hope. It is one of the strongest bridges yet between quantum mechanics and gravity, the two great pillars of modern science that have resisted unification for a century. If holography is true, it may guide us toward the long-sought theory of everything, a single framework that explains the smallest particles and the largest galaxies, the birth of the universe and the death of black holes. In this hopeful vision, holography is not only a strange speculation, it is a key to understanding reality itself, a compass pointing toward the deepest laws of nature. Cautionary vision, illusions without end. But there is another, darker possibility. What if holography is just the beginning? What if even the boundary itself is not fundamental, but a projection from something deeper still? We might be trapped in layers of illusion, like mirrors reflecting mirrors, never reaching the true original. In that case, the search for ultimate reality may be endless. Each answer only opens another shadow. Each discovery reveals another hidden wall of the cave. It is a humbling, even unsettling thought, that perhaps we are forever climbing toward a truth that can never be fully reached. Returning to the human place, so where does this leave us, as people, living our daily lives? It reminds us that our understanding of reality is always partial, always fragile. It teaches humility that the universe is stranger than we think, and maybe stranger than we can think. But it also reminds us of our unique role. We are the creatures who ask. We are the shadows that question the fire. We are the projections that turn back and wonder what surface we are written on. That act of questioning is itself profoundly human. Closing reflections. The holographic principle began with black holes, spread through mathematics, and grew into a possible framework for the universe. But its true power may lie in the questions it leaves us with. Are we shadows, or are we light? Is our world less real, or more mysterious? Are we confined within illusions, or joined within a cosmic unity? The answers remain hidden, but the search itself is meaningful. Because whether the universe is holographic or not, our curiosity connects us to it, and to each other. Perhaps that is the real message of holography, that meaning is not only in the destination, but in the endless journey to understand. If this journey through the holographic universe sparked new thoughts for you, consider leaving a comment. I'd love to hear your perspective. And if you'd like to keep exploring mysteries of science and philosophy together, Feel free to subscribe and join the conversation. After all, the universe is full of shadows waiting to be explored. If this journey made you question your place in the cosmos, leave a comment with your thoughts. Don't forget to like and subscribe. Your support helps us keep exploring the mysteries of reality.